In last class, we have discussed something about your model checking. So, what happens basically, it is a verification techniques, and in this verification technique called model checking, we are having three components basically. What is your modeling of the system, number to specification, basically you have to give the property, we have to give the property in some formal languages. So, that we can use some formalism to verify those property in the model, and the verification method that we are going to talk about your model checking. So, in last class I have introduced the concept of model checking with the help of an example, where we have seen that the designing of the mutual exclusion protocol. Now, with this particular small example, what we have seen that how to model a system, that means how to come up with the model of this particular system. Then we have to see what are the property that system or that mutual exclusion protocol should satisfy. We have note down those particular property like safety property, liveness property, then what we talked about non-blocking and no strict sequencing. Now, these are the property or these are the requirements for our system. Then what happens, those particular specification has to be captured in some formal way or in some formal language. Already we have discussed about CTL, computational tree logic, and we have seen how they have to be defined or expressed in your CTL. Then we have to see in the model, look into this particular specification. Now, we are going to check whether those specifications are true in this particular model or not. Okay, indeed, we have seen that the model that we have come up is not satisfying the liveness property, but we can modify it so that it can satisfy the liveness property also. Now, say with this small example we have seen, or I have given you the flavor how model checking works. Now, like that, when we are going for a bigger system, then we will be having lot of states, the state space will be more, and already we have seen that basically the number of states in our model will depends on the number of control signals that we have. It is basically exponential to the number of signals that we have in the system, which is equal to 2 to the power n. So, basically when we are going to look for a bigger system and we are having a complex formula or complex specification, how to check for the correctness of those particular specification in a model. For that we need some algorithm, we need some mechanized method, and today we are going to see what are the algorithms that we have for this particular model checking method. So, we are going to talk about model checking algorithm today. So, in last class I have also slightly introduced about this particular model checking algorithm. So, basically what we have in this particular model checking algorithm, we are having a model M. So, that system model M that we will be having, we will come up with this particular system model, and along with a one CTL formula phi, that means this is the property or the specification of the system. Now, how model checking algorithm is going to work? So, model checking algorithm provides all the states of model M which satisfy phi. So, basically you just say that we are going to give a model M and we will give a CTL formula phi, and we are going to collect all the states where this particular formula phi is true in the model M. So, basically ultimately we are coming up with a labeling algorithm. So, our basic aim is to find out a labeling algorithm. This labeling algorithm is going to label the states of this particular model with a formula if it is true in that particular state, and finally, we are going to return those particular states where this particular formula is true. So, this is about the model checking algorithm that we are going to look into it. So, basically what labeling algorithms, now we can look into the this way. CTL model checking algorithm basically works by iteratively determining, that is labeling states which satisfies a given CTL formula. So, here we are saying that it is work by iteratively determining. Okay, we will see, or iteratively we are having a iterative method which is going to label the states with the help of the formula where it is true. Okay. After that, after completion of this labeling algorithm, it will return all the states where the given formula is true. The basic input output to labeling algorithm are as follows. So, what is the input? So, we are having a CTL model M, and we know that this model is nothing but state of state, one transition relation and the labeling function. So, this is the input to the model, and where S is a set of states, that arrow is a transition relation and L is a labeling function. along with that we are going to give a CTL formula phi. So, what will be the output? The states of M which satisfy this particular phi. Okay. So, what is the labeling algorithm? Now, we have seen that what are the operators that we have, or temporal operators we have in our CTL, and there are basically temporal operator called next state, future, global and until, and these particular 4 temporal operators will come up with the path quantifier A and E. So, altogether we are getting 8 different combinations. So, we need the method for those 8 different combination or 8 different CTL operator. But already we have seen that out of those 8 we need only 3 which are going to form the adequate set of operators. So, if we know the method of 3 operators, then we can go for all those particular 8. So, we know that adequate set of operators, we are going to take one particular adequate set of operator which includes A f, E u and E x. That means, in all part in future there exists a part with until and there exists a part next step. Okay. So, we will just say that since this is the adequate set of operator, we are going to look for the method of these 3 particular operators, and so once I get the method for these 3 operators, then other can be expressed with the help of these 3 operators. So, when we are getting a particular formula phi shape, then first of all what we are going to do? We are going to express this particular formula in terms of the connective A f, E u and E x, because we are going to have method for these 3 operators along with the logical connectives and truth values true, because we are having 2 truth values true. One is true which is represented by top, and another one is bottom which is represented by false which is represented by bottom. Okay. So, we are going to look for the all logical connectives and the truth values true top and true which is top and false which is bottom. So, if any phi we are getting, any CTL formula phi we are getting, first we are going to express this particular CTL formula with the help of these 3 operators, because we know the equivalence, we are having some equivalence relation in CTL. Now, suppose psi is a sub formula of phi. Now, we are going to look for some sub formula. So, if psi is a sub formula of phi and states satisfying all the immediate sub formulas of psi have already been labeled. Now, what does it mean? Immediate sub formula means all the sub formulas that we have. So, basically what will happen when we are going to look for a particular formula? First of all, we know the components and we should know the truth values of those particular components. These are basically sub formulas. Once we know the truth values of the formulas or sub formulas, then we can look for the truth values of the main formula. So, as for example, I can say that a formula, say in our mutual exclusion formula, mutual exclusion protocol example, what happens? We have seen the Leibniz properties like that in AG T1 implies AF C1. Okay. So, this is a property, CTL property in AG T1 implies AF C1. Okay. So, say that in all part globally, if T1 is true, it implies that in all part in future C1 will be true. Now, in this particular case, you see that when we are going to look for this particular formula phi, then we have to come up with the all the sub formulas of this particular phi. So, here T1 and T2 are your atomic propositions. So, they will be CTL formulas. So, we are going to say that these are 2 CTL formulas. So, one I am having T1 and C1. Since these are your atomic propositions, so we are having that particular labeling function. We know that we have the labeling function, and with the help of labeling function, we label the states where the atomic propositions are true. So, we know the truth values of these 2 atomic proposition in our model, and we know in which state these are true. Now, once we know that these 2 are CTL formula, then we will find that AFC1 is also a CTL formula. Next, what will happen? We have to label all the states with this particular AFC1. Once we know the truth values of this AFC1 in all the states, then only we can go for the next level. So, that is why we are saying that first we have to look for all sub formulas. Once a particular sub formula is labeled, then we can look for the next one. So, once since it is a CTL formula, now with the help of our algorithm, we can look for the states where this particular formula is true. Then by looking into the main formula phi, then we are going to get this formula T 1 implies A F C 1. Okay. So, again this is a CTL formula, it is having two components A F C 1 and T 1. Now, again with the help of our labeling algorithm, we are going to label the states with this particular formula A T 1 implies A F C 1. So, this is also sub formula of the given formula. Now, all the states will be labeled this particular sub formula. Once we know the label of this particular sub formula, then we go for the next level, next sub formula, which is your A G implies T 1 implies A F C 1. Now, we know the level of this particular formula. So, we know the states where this particular formula is true. So, once we know this thing, then we can go for this particular our given formula phi. So, that is why I am saying that we must know the root values of our sub formulas. That means, we should know the states where this particular sub formula is true, and where this particular sub formula is true, we are going to label those particular states with the help of this particular sub formula with the help of our labeling algorithm. Okay. So, this is the way that we are going to look into it. So, when we are going to look for this particular phi, we should know the label or we should know the root values of all those particular sub formulas T 1, C 1, A F C 1 and T 1 implies A F C 1. So, once we know these things, then we can go for the complete given formula. Now, we are going to see what will be the algorithms to check for such type of formulas. Okay. Now, you just see that we are in this particular model labeling algorithm. What happens? We are going to give a formula phi and we are going to give a model M. So, we are going to define a satisfiability function, which is known as function set, and given input formula is phi and some model is by default, or we can define that it is set can be defined like that, set satisfiability in the model M and the given formula phi. Okay. Now, in this particular case, now as per the semantics of this particular CTL formula, what happens? We know that all states will be labeled with your root value true and none of the states will be labeled with the root value false. So, that is why if phi is true, then it is going to return the complete state space S, because true is true in everywhere. If the phi given formula phi is your false bottom, then it will return the null set. So, this is basically nowhere it is true. So, it is going to return the null set, because the root value false is false everywhere. So, no, it will not label with this particular false. So, if my given formula is your phi, then it is going to return the null set. Now, if phi is atomic, so now we are giving some atomic phi is equal to say some atomic variable p, then what will happen? Then it will return the states, those particular states where that state is a member of this particular labeling function of this particular state, because we know that all states will be labeled by your atomic proposition. Okay. So, with the help of labeling function, we are labeling the states. So, if my given formula phi is an your atomic proposition, if it is atomic, so it is going to return all such type of states which are a member of this particular labeling function for that particular state S. Okay. Now, if my given formula phi is negation of say phi 1. So, it is I am giving a formula phi which is a negation of phi 1. So, you just see that I am saying negation of phi 1. So, when we are going to look for this particular formula, so phi 1 is a sub formula of this particular given formula. So, we must know the label of phi 1 in each and every step. So, if my given formula is negation of some CTL formula, then what it is going to returns? It is going to returns the states where this particular phi 1 is not true. That means, first we are going to have the label of the states where phi 1 is true, then the remaining state will be your not of phi 1. So, it is going to return S minus set of phi 1. So, this satisfiability of phi 1 is going to give me the states where the given formula is true. So, for negation of phi 1, it will be S the total state space minus satisfiability of phi 1. Okay. So, just see that if not of phi 1, we can say that it is having a sub formula of phi 1. So, first we know the labeling of phi 1, then only we can go for the not of phi 1. Similarly, if phi is your phi 1 and phi 2, this is the logical connectives, then what happens? It is going to return the set. First we know the labeling of phi 1 and phi 2. So, it is going to return me two states. two sets. So, the intersection of these two states will be the states where this particular formula phi 1 and phi 2 is true. So, satisfiability of phi 1 is going to give me a set where the formula phi 1 is true. So, this is one state, I can say that in this particular state phi 1 is true, and satisfiability of phi 2 is going to give me another set, it is going to say that where the formula phi 2 is true. Now, for this particular phi 1 and phi 2, that phi 1 and phi 2 must be true in both are true in that particular state. So, intersection will give me this particular state. So, it is going to return me this particular intersection point. So, similarly, phi 1 and phi 2, phi 1 or phi 2, it will union of these two states. Again, we know that if it is a phi 1 implies phi 2, then return not of phi 1 on phi 2, because this is equivalent. We know that phi 1 implies phi 2 is your equivalent to your not of phi 1 or not of phi 2. So, that is why just we are going to look for the satisfaction of the satisfiability of these things, and ultimately we are going to get this particular step. Now, we know this particular formula that A x phi 1 is equivalent to not of E x not of phi 1. So, we have seen this particular equivalence. So, if my given formula is A x phi 1, then we are going to look, it will return going to look for this thing satisfiability of not of E x not of phi 1. That means, first we have to express this particular A x in terms of E x, because we are going to look for a minimal set of operators which involves E x, another operator which is going to have E u, and third one is your A f. So, this is the minimum set of operators that we are going to look for it. So, A x will be represented with the help of E x. Now, it is E x phi 1. Now, I am going to say that there exists a part next step phi 1. Now, what happens? For that, it is going to return satisfiability with this particular E x phi 1. Now, you just see that in other cases we are expressing it by some other things. Now, for E x, now this is a operator. Now, this is the member of my minimal set of operators. This is the minimal set or adequate set of operators. That means, I need a method for E x now. We look for this particular E x. Similarly, if it is a phi 1 until phi 2, then we have discussed while discussing about the equivalence of CTL, that can be represented that a phi 1 until phi 2 can be expressed with the help of E u, okay, or E g. So, this is the equivalent formula. So, when it is a phi 1 until phi 2, then we are going to look for the satisfiability of this particular formula. Okay. Now, when E phi 1 until phi 2, then when my input formula phi is your E phi 1 until phi 2, then we are going to return satisfiability E u phi 1 comma phi 2. That means, we need a method for this particular operator E u, this because it is in my minimal set of operators. Now, when my given phi is your E f phi 1, then we are going to look for E t until phi 1. So, true until phi 1, because we know that futures can be expressed with the help of your until operator. So, if it is your E f, then we need this particular E true until phi 1. Similarly, if it is your A g E g, then what will happen? E g phi 1, this satisfiability of E true until phi 1. So, A f, so we need a satisfiability function like that. A f is your satisfiability A f phi 1. So, since it is a member of my this particular minimal set of operators, so I need a method for A f. So, this is another method, and we need one method for set E u. Okay. Similarly, A g can be expressed with the help of this equivalent not of E f not of phi 1. Now, now, any kind of formula I am giving as an input to this particular function set, then it is going to give me the set of states where this given formula is phi, given formula is true. Now, for that, since this is the minimal set of operators, so we need the method for this particular 3 operator E x, E u and f, and in this particular 3 position, we are going to call the appropriate method. So, what we have seen that whatever phi that we are having, so if we have any CTL formulas, then we are going to call the appropriate sub formula, we will convert it to the appropriate sub formula and we are going to get the state of state where this particular given formula is true. And since this is the minimal set of operators, so we need the method for set of E x, set of E u and set of A f. Now, we are going to discuss about these three procedures, what will be the algorithm look like for this particular E x, E u and A f operators. So, it is if we are having an atomic proposition P, then it is very simple. We are going to label states with P if P is a member of LS, because you just see that we are having these things. If it is atomic, then we are going to return all the states where it is a member of this particular labeling function. So, we are going to say that if given your formula is your atomic proposition, then we are going to label the state S with P if it is a member, P belongs to your LS, labeling function of a particular state S. Now, similarly, if we are having any logical connectives say P and Q, then label S with P and Q if S is already labeled with P and Q, because we have seen this particular thing. If it is your P phi 1 and phi 2, then we are going to look for the intersection of these two states. So, what will happen? If it is we are going to look for this particular P and Q, then we are going to look for the states where both P and Q are true. So, if S is already labeled with your P and it is also labeled with Q, then we can label this particular state as with P and Q. So, like that we can go for any other logical connectives. Now, temporal operator we are going to look for say E x. This is one of the temporal operators of our minimal set of operators or the adequate set of operators. So, in this case it is there exists a part in next state P is true. So, label any state with E x P if one of its successor is labeled with P. So, label any state with E x P if one of its successor is labeled with P. So, we are going to see the entire state space. So, in case of E x P, so P is a sub formula. First, we know the labeling of this particular P. If you know these things, then we can go for this particular given formula. So, label any state with E x P if one of its successor is labeled with P. Okay, just select one example. So, this is a model. You can say this is the Kipke structure. So, these are the state of states. So, we are having from S0 to S6, okay, S0, S1, S2, S3, S4, S6. Now, say that with the help of labeling function, this S3 is labeled with P and say S2 is labeled with P. That means, we are going to get a set where S2 and S3. So, in this state of states that P is true, because these are labeled with this particular P. P may be atomic proposition or it may be any sub formula, because when you go for E x P, we must know the label of P. So, P may be any CTL formula. Okay. Now, what we are saying that label any state with E x P if one of its successor is labeled with P. So, in this particular case, if you see these things, now if you come to S0, then it is having two successor S1 and S2. So, one of the successor is labeled with your P. So, it is a member of this particular state. So, for E x P, what will happen? We will get that S0 will come into this thing. When we come to S1, we will find that it is having one transistor and this particular state S3 is having this marked with labeled with P. So, we can say that S1 will be labeled with your EXP. Now, when we come to your S2, it is having one successor S4 which is not labeled with P. So, S2 will not be labeled with EXP. When we come to your S5 or S3, then what will happen? You just see that it is having two successor, one is S6 and second one is your S0. So, we will see both the successor, none of the successor is labeled with your P. So, S3 will not be labeled with your EXP. When you come for S1, S4, it is having one successor S6 and it is not labeled with P. So, it will not label with your EXP. When we come for S6, it is having successor S6 itself, it is not labeled with P. So, it will not label with EXP. So, basically we are getting these two states S0 and S1 where EXP is true. So, the satisfiability algorithm or that labeling algorithm will return this particular set of state S0 and S1 and it will say that in these two states my EXP is true. Now, this is the algorithm. You just say that what is the function? It is function EX satisfiability SAT EXP. That means find out the state of states where the formula EXP is true. So, we are going to look for the formula EXP. Determine the set of states satisfying EXP. Now, here we are taking two local variable x and y. Now, what is x? X first we are going to say that it is calling this particular function satisfiability with the sub formula P. So, it is going to return the state of state where this particular P is true. So, like that if you are going to look into this thing. So, this is the set x S2 and S3. Now, what we are going to do? We are going to collect all those particular state S0. So, it is some sort of S0 which belongs to that particular set of states of my model in such a way that there should be a transition from S0 to S1 for some S1 belongs to X. So, in X what happens? We are having all the states where P is true. So, now we are going to collect all such type of state S0 where from this particular state S0 we are having a transition to the member of this particular state X1. That means, we are going to get some distinct states where in next state this particular formula P is true. Then after looking into it, then we are going to return this particular set of state Y. So, basically this particular steps is going to give me a set of states where the formula EXP is true. So, this is a very simple algorithm. So, giving the formula and if we know what is the sub formula P. So, we must know the labeling of this particular sub formula P. So, we are first going to collect those particular states and we say that this is my X, okay, because we are going now calling this particular satisfiability function with the P only or EXP. So, once you get this thing, then now we can collect the other state where that EXP is true. Okay. So, we are going to look for all such type of transition where S1 must be a member of this particular set X and what is the set of this set X? This is the states where the formula P is true. Okay. So, this is a very simple method. So, like that in previous example, here we can say that first X is your S2 and S3. Now, from here from those particular state we are going to look all the predecessor states. So, it is going to give me S0 when it is your S3, then from here we are going to look all the predecessors where it is going to give me your S1. So, these are the two states where this particular formula EXP is true and this is the Y that we are having, set Y that we have defined as a local variable. So, next operator is your AFP. Okay. What is AFP? Basically, in all path in future P must be true. So, wherever you go, we must get an states in future where P is true. Now, how we are going to get an algorithm for this particular operator? You just see that we are saying that if any state S is labeled with P, label it with AFP. Now, say if we are going to look for AFP, then P is a sub formula, we must have the label of P. So, we are saying that if any state S is labeled with P, then label it with AFP. Why we can do these things? Already we have defined the semantics and in our semantics what we have seen that future behavior includes the present scenario also. So, basically if you look into the timeline, say this is my present and these are my future direction and that is my past. Okay. Now, while defining our semantics, what we have seen that the future behavior of the system includes the present behavior also. So, that means my future is from this particular present scenario. So, this is as per the semantics that we have defined. Since if P is true in present state, we can say that it will be true in the future also. So, if any state S is labeled with P, we are going to label with AFP. Okay. So, this is the first step we are doing, then we are going to repeat it like that. Label any state with AFP if all successor states are labeled with AFP until there is no sense. So, now what will happen? First, this is our base condition is that set of states where P is true, we are going to label those particular states with the formula AFP. Then we are going to repeat our procedure, label any state with AFP if all successor states are labeled with AFP until there is no sense. That means, we are going to collect the states iteratively, and if you cannot include any more states, then we can stop at that particular point. So, this is the saying that until there is no sense. So, see why we can do these things, because we have seen one equivalence that AFP, we can write AFP with the help of this equivalence, that P or AX AFP. What it says that if P is true in a particular state, then we will say that AFP is true. So, this particular P is captured by this particular my first condition. If any state S is labeled with P, label it with AFP, and this is possible because my future includes the present behavior. And what the next component we are saying that either P is true in this states, or we are going to say that in all part next state AFP is true. So, that means, if this is your either P is true over here, or whatever states we are going to get, say here, in all state AFP is true. So, in all part next state AFP is true. So, like that, if it is there, then we can include this particular state of states where this given formula AFP is true. So, that is why I am saying that label any state with AFP if all successor states are labeled with AFP. Okay, we are iteratively going to label it. So, if I am labeling those particular states with your AFP, because if P is true in all those particular states, then we can very well label with your AFP. So, in this particular case, we can label this particular state with AFP. So, that is why we can say that, and like that we are going to collect each and every state. That is why we are saying that we can repeat this particular procedure until there is no sense of the state of state that we have collected. So, this is done with respect to this particular equivalence. If P is true, that means this is the first step, and we are repeating this particular second step for those particular portion. Okay. Now, you just see that this is the given level. So, we are saying that just as an example, we are saying that these are the three states where P is true, that means it is labeled with P, and this one is not labeled with P. Now, according to this particular first one, we are saying that if any state S is labeled with P, label it with AFP. So, since P is true in this particular three states, so we are labeling with AFP. Okay. This is the first step. Then we are going to repeat our procedure. So, we are going to do it until there is no sense. Then what will happen? Since we know that AFP is true in this particular three states, we are going to look for its predecessors. Since this predecessor we are getting 1, and from here we are saying that in all those particular three states AFP is true. So, we can label this particular state with also AFP. Okay. So, this is the way that we are going to learn. So, if we have some more states over here, then what will happen? So, like that we can go backwards. So, if I can have some more states. So, once we know the level of these things, then we can go for the level of those particular states also. We will proceed in this way in backward manners, and until there is no sense. That means, we cannot collect any more states. That means, what happens? You just see that initially my this particular where is AFP is true, I can say that it is true is your S0, S1, S2. So, these are the three states S0, S1, S2. Now, when we have done this particular step, say this is my S4, that means the set of states where this particular formula is true becomes S0, S1, S2 and say S4. Like that we will proceed, and unless we cannot include any more states in this particular state, then we will stop there, and we are going to return this particular set of states by saying that these are the states where this particular formula AFP is true. Okay. So, this is the basic concept. Now, after having this particular concept, now what we can do? We can look for the algorithm. So, this is a simple algorithm that we are having. So, this set of AFP is going to determine the set of states where this particular formula AFP is true. Now, like your previous case, we are going to take help of two variable x and y, and what is this x? First initially we are initializing x to all the states, basically this is the complete as we are taking, we are saying that this is the complete state space we are initializing to S. Okay. And what is your y? Y is your calling this particular satisfiability function with this particular formula phi. Okay. Phi is a initial formula and it is the sub formula of this particular given formula. So, basically we know the label of this particular formula P. That means, when we call this particular procedure satisfiability with this particular sub formula P, it is going to return me those particular states where the given formula P is true. Now, what happens? So, wherever P is true, we are going to say that AFP is true. So, what we are doing? So, we are saying that now y is assigned to x. Okay. So, just saying that initially in all those particular state y, the given formula AF is true. So, this is in one step we have getting some state where this particular formula AF is true. So, we are just keeping this particular information x. Okay. Now, and we are going to do this particular loop until x equal to y. So, initially we are having some state y where this particular formula P is true and this is the whole state space. So, they may not be equal at the very beginning, provided in all states are marked with P. Okay. So, until x is equal to y, we are going to repeat it. So, what we are doing? We are keeping the previous information, because in all state y AFP is true. This is according to my first condition. If any state S is labeled with P, then label it with AFP. So, this is my first condition. So, according to first condition, in all the states of this particular y are labeled with AFP. So, we are getting this initials. And what we are going to check now, y will be updated now. Now, what are the states that we can include in this particular state y? You just see that if we are having such type of scenario, if all the next states are labeled with your AFP, then we can very well include this particular state to the set of states where AFP is true. So, that is why we are having this particular loop sentence, y will be updated now, y union, what are these things? We are going to loop for all such type of states where we are having a transition from this particular S to all such type of S dash, and where S dash is a member of y. Okay. So, this is the basic scenario. Actually, we are going to look for such type of state S4, and we are going to look for all the transition and all the next states that we are going to have, their AFP must be true over there. So, that means they are the member of this particular set y. Okay. So, that is why you are saying that all such type of S dash we are going to look, and those all S dash must be a member of y. That means, in all those particular S dash AFP is true. So, we are now appending this particular y with those new states. Okay. Again, we will repeat this particular loop, and we are going to check whether x equal to y or not. If in any of this particular scenario, if y is not updated, then x and y remain same. So, at that particular case, we can terminate this particular procedure. You just see that we are collecting, going from the particular set of state where P is true and traversing the whole graph and collecting all the things. If at any point of time we cannot include any more states, it is going to say that now you stop here itself, because now there is no possibility of including any more states, because you just see that I will tell you one example. Say you are looking for in all part in future P is true, just do not say that P is true. This was marked with P. So, these are the state S0, S1, S2, S3, S4, S5, S6, S7, S8. Now, as per our distance algorithm, the first step we are going to start with your S4 and S5. So, these are the two states. So, now this is the basic state. Now, we are starting with S4 and S5. Now, we are going to look for those particular predecessor state. Now, we are coming to this S 1 wherever you go in all. So, this will be labeled with your AFP, this will also labeled with AFP. So, in all state I am coming to this particular state and we are saying that we are getting one particular state S for only one state which is labeled with AFP. So, I can include this one S 4, S 5 and I can include now this S 1 also. Okay. Similarly, when S 5 is also member over here, then what will happen? I am going to get one predecessor state. So, I will give for complexity, I will give one more transition. So, we are giving coming to S 2. So, there is only one successor state where it is labeled with your AFP. So, I can include this particular S 2 over here. Now, this particular S 5 having another predecessor S 3. Now, when we coming to S 2, you will find that it is having two successor, one is labeled with AFP, one is not labeled with AFP. So, S 3 cannot be included. So, we are coming to this particular side. Now, in this particular case, what will happen? Now, Y is updated from S 4, S 5 to S 4, S 5, S 1, S 2. Now, we will go into the loop. Now, what will happen in this particular case? Now, these two members are newly added. We are going to look for the predecessor. So, S 1, S 0. Now, in S 0, we are having three successors S 1, S 2 and S 3. S 1 and S 2 are labeled with your AFP, but S 3 is not labeled with your AFP. So, we cannot label S 0 with AFP. So, in this particular case, my states remain same. So, there is no sense. So, at that particular point, we can stop our procedure and we will say that these are the 4 states where we are going to include, because in this particular case since no more states are including over here. So, there is no possibility of getting any more steps, because we are going to see all the predecessors. That means, if someone is not member over here, that means it is not a member of your AFP, like that say S 8, if you say these things. So, what will happen? From S 8 we will go to S 7 and P is not true over here. So, we are not going to get any part where in future P is true. Otherwise, if P is true here, then in the very first case P would have included over here also. So, there is no chance that any more states will be included over here. So, if there is no sense in this particular set of states, that we can stop the procedure there itself. Okay. So, this is why we are saying that until there is no sense. So, eventually we are coming up with a very elegant procedure. So, this procedure can be now implemented. First collect all the set of states where P is true, then repeat this particular loops. Okay. Now, another operator, that temporal operator or CTL operator that we need is your EP until Q. Now, how we are going to see that EP until Q, there exists a part where P remains true until Q becomes true. Now, again you see that according to our semantics, that future includes the present behavior. So, that is why the first step is coming. If any state S is labeled with Q, label it with EP until Q, because future includes the present behavior. So, if any state is labeled with your Q, we can say that EP until Q is true over there. So, we are going to label this particular state with EP until Q. Now, we are going to repeat this particular procedure. Label any state with EP until Q if it is labeled with P and at least one of its successor is labeled with EP until Q. Okay. So, P should remain true until Q becomes true, and we need at least one path. So, that is why we are saying that at least one of its successor is labeled with EP until Q, and P must be true at that particular point. So, if the state is labeled with P and if you will find that any of the successor is labeled with EP until Q, then we can label this particular state with EP until Q, because if any one of the successor is labeled with EP until Q, at least we will say that in future somewhere Q is true and till that particular point P remains true. So, that is why we can say that first is any state S is labeled with Q, we are going to label with EP until Q and we are going to repeat this procedure. Why this is possible? Because we have seen this particular equivalence. Okay, already we have seen this particular equivalent. What we are saying that EP until Q can be expressed as Q or P and there exists a part next state EP until Q. So, this is you shall see that if P is Q is true in S, we are going to label with P until Q. So, this is the first part, first disjunct. If Q is true there, then we are going to label with E P until Q. So, if Q is true, then fine, we are going to get those particular state, and if it is said or, we are going to have this particular condition. So, this is the second clause or that repeat one. P must be true in that particular state, and there exists a part in next state, it is labeled with P until Q. So, from this particular equivalent, we are developing this particular method. So, and we are going to repeat it until there is no sense. So, we are going to collect states one after another, and we are going to stop in a particular point where we cannot include any more states. So, we are going to say that until there is no sense. So, this is the equivalent. So, from this particular equivalent, we have got a method for E P until Q. So, just say that simple example I am saying, that similar example I am taking. So, these are the three states. Initially, we are having say S 0, S 1, S 2, S 3. Now, as per the first condition, wherever Q is true, we are going to label with E P until Q. So, by looking into these things, what will happen? We can label this particular state S 1 with P E P until Q. Okay. So, this is the only state where Q is true. So, we can label it with P until Q. Then what will happen? Once we know the label, then we can traverse the graph, and we can say that we are going to, for this particular state, we are going to look for the predecessor here, and if this is labeled with P, then we can label it with P until Q, because it is labeled with P and any one of this particular successor is labeled with E P until Q. So, P remains true until Q becomes true. So, since Q is true, we are labeling with your E P until Q, and we are coming to this particular state, and we have seen that P is true. So, we can label it with E P until Q. So, this is the way that we are going to traverse the graph until there is no sense. Okay. Now, look into the procedure. So, we are going to get an elegant procedure for this particular E P until Q also. So, we are going to have a function satisfiability E until P and Q. So, we are going to take now three variables W, X, Y. Now, we are having sub formula P and Q, because we are going to look for E P until Q. So, this is one sub formula, this is another sub formula. So, in W, we are going to say that going to call this particular satisfiability function with P, because we know we must know the level of P. So, this is the set W. X is basically we are going to send the entire state space, X is equal to S, and Y is your satisfiability of this particular Q, sub formula Q. So, we are going to collect all the states where Q is true, and we are going to say that this is my particular set Y. So, Y is set of state where Q is true, and W is your set of state where this particular formula P is true. Now, we are going to repeat this particular loop. Okay. Now, what it says that Y, if you are going to look into Y, is the states where this Q is true, and we have seen that wherever Q is true, we are going to say that P E P until Q is also true. So, if any state S is labeled with Q, then we are going to label with E P until Q, and this is because of our definition of semantics, because future includes the present behavior. Okay. So, that is why this is the set of state where E P until Q is true. Now, we are going to collect the states where it is true, and we are going to append this particular state Y. Now, what will happen, since this is a set of state, now we are going to say that these are the previous condition we are going to keep. So, in set of state Y, P until Q, E P until Q is true. So, we are just preserving this particular set of state in X. Now, X has sense to S to those particular state. Now, we are going to append this particular Y. So, how we are appending it? This is your Y union. That means, now we are going to look for those particular states where our given our required condition is satisfied. So, it should be such thing like that W. What is W? This is the state of state where P is true. So, W intersection, we are going to collect all such type of state S, such that from S to S dash we are having a transition, and this particular S dash is a member of Y. That means, in S dash we are going to see that it is already E until E E p until q is already true in this particular state of S. So, if we are having a transition from this particular set S to the set of states where E p until q is true. So, any states where p until q is true and we are having a transition from S, then we can say that in S E p until q is true. Okay. So, that is why we are appending it. So, we have, and second condition is in S p must be true. So, that is why whatever states we are collecting, along with that we are intersecting with the W. In W it says that the set of states where p is true. So, that p must be true, and whatever states we are getting over here, we are appending with this particular y, and we are going back to this particular repeat statement. We are going to check whether x equal to y or not. What we have in x, this is the previous set of state where your E p until q is true. Now, we are going to check whether any new more your states has been added or not. If it is added, that means these are not equal, then again we will go into this particular loop and we are going to collect. So, you just see that this is the procedure we are having, and this is nothing but the graph traversal algorithm. First, we are going to start from some states of this particular graph, and we are going to look for all the predecessors. If my given condition is true or given situation is true in this particular predecessor, we are going to include those particular set also in my set of states. Then again I will going to repeat this thing. So, whatever new states we are including, we are going to form those particular states, again we are going to look for all the predecessor. And if not any new more states cannot be added to this particular state, then we can say that we are not going to get any more state, and this is the final set of state we are going to get, and that is why we are returning this particular set of state y. Okay. So, these are the set of states we are going to see. So, in your CTL model checking algorithm, now what we are going to have? We are saying that after performing the labeling for all the sub formula phi, including phi itself, we output the set of states which are labeled with phi. So, finally, we are going to give those particular set of states where it is true. So, you just see that we need the minimal set of operators. Here we are considering E x, A f and A u. So, we are simply seen how this can be implemented, and we have got very elegant algorithm, elegant procedures to implement these three operators. So, once we know the algorithm for these three operators, now others can be expressed with the help of these three. Okay. Now, what will happen? Now, we have to look for each and every sub formula, and once we know the sub formula, then only we can go for the main formula. So, that is why you can say that what is the time required to do this particular model checking. If you find that, you can say that the time complexity of the algorithm will be your order of f and set of states, and this is the complete graph V plus E, that means set of state and set of transition that we have. This is basically I have said the number of connectives in the formula, that means number of sub formula that we have. Basically, you just see that if I am going to say that phi 1 and phi 2, I have to call this algorithm in 2 times, because first I have to look for the phi 1, then we have to look for the phi 2. We know the labeling of these two, then only I can go for the conjunction of these two things. So, that is why I said that it is a number of connectives, or we can say or the length of the formula that we have over here, because when I give this particular formula, we must know the truth values of phi 1 and phi 2, then only we can look for this one. And you see that first we are collecting some particular states. From that particular states, we need to see all the predecessor state. In AX, this is only one level, but in case of AF and EU, we have to iteratively we have to look for this particular thing. So, from all states, at least we have to look for its predecessor, and E is the number of transition. That means, in worst scenario, you have to traverse the complete graph actually. So, that is why we are saying that this is the complexity of my labeling algorithm. So, this is your linear to the length of the formula, and this say that quadratic to the number of nodes that we have in this particular graph. So, this is simple graph traversal algorithm, and the time complexity depends on the length of my formula, because for every sub formula I have to call these particular procedures, and we have to look for each and every state of this particular, in worst scenario you have to look for each and every state of this particular graph. So, this is basically we are going to have a linear time algorithm for this particular procedure. So, this is the beauty of your CTL model seeking algorithm. So, and it is easy to automate. So, these are the basic 3 algorithm we have seen, and next class we are going to see some example, we will explain and we will see how we are going to, or we will see the execution trace of those particular algorithm. In next class again we will going to discuss about these 3 operators only with the help of one examples. Okay. I will stop here today.